So welcome to the seminar series in the Gemini Center on Quantum Computing. Today we will have a talk about quantum resistant cryptography from lattices by Hans Heum. And he is currently a researcher at NTNU, which means, according to him, that he's a postdoc yet to defend his PhD thesis. He did his PhD thesis at Simula UIB in Bergen, specializing in provable security or public key encryption schemes. Before that, he did his master's in theoretical physics at the University of Bergen, specializing in phenomenological models of supersymmetric quantum field theories. So without further ado, please go ahead and take it from here.
Thank you very much. So first of all, Nadia, would you mind muting your microphone?
Sorry.
That's okay. Thank you. All right. So I'm going to be doing a very introductory showing how we construct quantum resistance cryptography from lattices. So we only have roughly 30 minutes, and I'm hoping I'll be able to get through all of this in time. But apologies if I have to go a bit fast towards the end. And this was a question that was posed at the meeting we had here in Trondheim. Somebody asked, well, how do you actually make crypto from this? And I quickly realized that that would take way too long to answer. So we made it into a seminar instead. So without further ado, I have drawn a three-dimensional lattice here. Oh, wait, something is not working. Okay, my pointer is not working, but that's fine. So I have drawn a three-dimensional lattice with some arrows, and I'll talk about what these means in a minute. But first, I will do a quick recap of post-quantum cryptography. So most of you probably know this already. We have in 1994, Shor came up with his famous algorithm, which can factor large numbers, as the quantum computer I've drawn on the right here is happily doing. And it can also break most other kinds of public key cryptography that was being used today. So that means we need new crypto. In 2016, NIST, which is the National Institute of Standards in the United States, announces their post-quantum cryptography competition. In 2017, 82 submissions were submitted, and they built on a variety of hardness assumptions. And you both had public key systems called CHEMS, which is an acronym for key encapsulation mechanism or key exchange mechanism, and DSA, which is a digital signature algorithm. So last year, one CHEM was chosen and 3 signature algorithms were chosen. And what is noticeable about the winners is that all of them, except for one of the signature algorithms, are based on lattices. So this really is the big player in the game as far as directions for the science of crypto systems goes in the post-quantum world. Oh yes, and I had an official silver medalist at the QCrypt 2019 Limerick competition, which I am very proud of course. Your secrets are safe, you're sure, with RSA 1024, but what you don't know, in my basement at home, I got 10,000 qubits on Shore. Now it should be 20 million, but 10,000 sounded better. All right, so to go into the nitty-gritty, this is going to be a lot of, it's essentially an exercise in linear algebra. So it will quickly become a bit technical, but it will never become, more than undergraduate level math. So I hope you're able to follow. But first off, the hard problem, in order to make public key cryptography, I should say, asymmetric cryptography, we need what we call a one-way function, something that is easy to compute in one direction and hard to compute in the opposite direction. And here is an example of a one-way function. On the left, I have a lattice, and I have drawn one with a with a normal, what is it called, orthonormal basis on the left, which is sort of like a nice basis, and one with a rather ugly basis on the right, which is, if you have a nice basis, it's always easy to transform it into three ugly vectors that are also a basis. But going in the opposite direction is hard in general. Now I've drawn this lattice. I noticed now that I've drawn this lattice so that they actually align with the axes, which I believe would make the problem easy. So in general, the lattice would be skewed and squished in different directions, and you would have way more than 3 dimensions, something like hundreds or maybe even thousands of dimensions, which are difficult to draw. So the hard problems that we use, the first one is called the shortest vector problem. So that is, given one of these ugly bases, find one of the shortest vectors in the lattice, right? So just a vector going from the center to one of the lattice points, and it needs to be shorter than some threshold. You also have the closest vector problem, where you put some marker somewhere in the space, and you want to find the point which is closest to that marker. Once again, easy to do if you have a nice orthonormal basis. Here you see you just go up 1 and minus z direction by 1. But if you have this ugly basis on the right, it's in general hard to solve this problem. The problem that we will be looking at today is called the learning with errors problem, which is shortened to LWE. And most of the crypto that is winners of the NIST competition is based on LWE problem. I have less of a pictorial intuition about what the LWE problem is, but it is known to be at least as hard as many of these lattice problems, meaning that if you can solve the shortest vector problem, for instance, then you can solve the learning with error problem. Or, yes. All right. So to get into the nitty-gritty, we start with learning without errors, which is, you know, a crypto system, which is not safe. So just to introduce some notation, first of all, we do all our arithmetic in mod Q. So this is all modular arithmetic. Because of this, it will be useful to have a notation for the integers between minus, for instance, beta and plus beta. So we have this square bracket, meaning from minus beta to plus beta, integer values. And we use this arrow with a dollar symbol to mean that we uniformly sample an element from S and assign it to the variable A. So let's start with an assumption. So this is the sort of security assumption that we will build our crypto system on. If you have a uniformly sampled matrix and a uniformly sampled short vector S, so beta is now a small value, so S will be a short vector. And if you uniformly sample a vector U, which does not have to be short, then assume the following. An adversary can't tell whether you give him the matrix A and the transformed short vector S, where you have applied A to S, or whether you gave the matrix A and a uniform vector U, which has no relation to A and short vectors. Another way of posing it is if you apply the inverse of A to U, will the result be a short vector, right? Okay, so now with this assumption, we let the secret key be this short vector S. We let the public key be the matrix A, and the short vector transformed by the matrix A into something that is no longer short. Now, what we do to encrypt is that you sample some random element R, which is also short, but it's I see that I am missing an arrow here. So R is a vector, so it's an n element vector. I should also mention that A is an n by n matrix. I think the previous slide said so. So everything is dimension n in this case. So you sample this random vector R, but where each element is small, so within this limit of beta. Then you compute your U, which is just A applied to R, but transposed in a way. And then you compute this scalar value V, where you apply this A times S, plus the bit that you want to encrypt, which is B here. So you see that the A and the AS are public, is actually the public key, as you see on the top of the screen. And then you send these values. Okay, so for now, this might seem somewhat arbitrary, but we will see that the receiver who gets these values, U and V, can compute the value V minus U vector times S vector, or inner product. And this S vector is now the secret key. So this is why anyone cannot do this. And then you just unpack our notation that we have introduced. V is RTAS, as you see up there. Then you get plus B from V, and then you subtract RTA and S, which was multiplied by the receiver. And you see that the two terms cancel, and you are left with the bit you wanted to encrypt, namely B. So great success. And then the question is, how would you break our system? I sort of already gave the answer previously, but of course you just use linear algebra to solve the equation A times S equals U. You have been given something. You have been given A, and you have been given A times S, which is equal to U. And then you just solve this using normal linear algebra techniques. And then you see whether S has this property that all of its elements are smaller than the absolute value of beta. In particular, if there are several solutions, then you pick the one that has fulfills this property. And then you have computed the private key, the secret key, only given the public key. So of course, this crypto system is completely insecure. So pictorially, what you have done is that you've taken a long random vector and you've just reduced it by applying the inverse of A, and then you get a short vector, which is equal to the secret key, right? Easy peasy. So we need something better. So this is where learning with errors comes in. And this is where we introduce this error term, which is the new vector at the bottom here. The rest is just copy pasted from above. So exactly the same. You have n by n matrix A, a secret vector with short elements, and a random vector with uniform elements. You have this vector E, which is also short, and which is called the error. And then the new assumption is that the adversary can't tell whether you gave them A and A applied to S, then perturbed by this small error vector E, or whether you gave them A and a uniform vector. So in a way, if the previous assumption was that you were given a uniform looking vector that hit exactly, at one of the lattice points, then maybe you can think of this as having been perturbed a little bit out of the way, so that it's not as easy to just apply the inverse and find a valid short vector. Now, once again, take these drawings with a pinch of salt, because this is just me trying to understand the problem, and I'm not entirely confident that this is accurate. Regardless, the crypto system is looking very similar to what we had before. The secret key is this short vector S. The public key is the matrix A and A times S as before, but now perturbed by this small error. And you again want to encrypt a single bit. So you do as before, you sample R vector, apologies for missing the vector sign, which is, again, has short components within absolute value of beta. You sample a new error term, not the same one as the previous one, so that's why I call this E1, which is also a vector, and then you sample a second error term, which is a scalar, so just a single value within absolute value of beta. Your encryption now is to compute R times A plus the first error vector that you sampled, and then the scalar value, which is R times essentially the public key, right? A times S plus E. And then you add the second error term, the scalar value that you sampled, and then a bit weirdly, you add the bit again, but now you multiply it by Q divided by 2. You will see in a bit why this ends up working pretty nicely. But remember that Q is the modulus that we operate over. So Q plus 1 equals 1, for instance. So then you send this ciphertext, U vector and V, and then hopefully we are, as receivers with access to the secret key, able to recover the bit B. So let's see how you do this. You receive the U vector and the V. As before, you compute V minus U vector times S vector, where again, S is the private key, which is why only the receiver is allowed to do this computation. And then you just unpack what I wrote on the previous page. So on the left here is essentially I've just copy pasted what I wrote as RV. And on the right-hand side, I have copy pasted what we wrote for U. So in particular, you see as we unpack this, on the left, you get an RTAS term. And on the right, you also get an RTAS term, which is exactly as we had with our previous non-secure version of this crypto system. However, you are also left with a bunch of error terms, which do not cancel. So then what? Well, here's the trick. You notice that all of these were sampled so that their elements are smaller than beta. So in the worst case, you get something that is of size beta times size beta, and then these are, n length vectors. So you multiply by n in the worst case if all of them are equal to beta. And you get something which is bounded by n beta squared plus n beta squared plus just beta for the scalar term. So then you can rewrite this as an E hat, I've chosen to call it, which is an error term, which is bounded exactly by this value 2n beta squared plus beta. Somewhat arbitrary value, but that's fine. What we have to recall here is that beta is supposed to be small. In particular, it's supposed to be small compared to Q, the modulus that we are working over. So we can set our parameters when setting up the system so that we are guaranteed that this value that we end up with, 2n beta squared plus beta, is smaller than the modulus Q divided by 4. Now, why would we want that? Well, it's maybe easier to see what's going on if we view, instead of like a number line, we view this as a clock, as you often do with modular arithmetic. And remember that if 0 is on the top, then plus minus Q half is on the bottom. So that's, in a way, Q half is the value that is most removed from 0. And then Q4 and minus Q divided by 4 are on either side. Now, we guarantee that our error is in the top half of this circle by saying that it should be smaller than the absolute value, or the absolute value should be smaller than Q over 4. And now, because we multiplied our bit by exactly q/2, if the bit was equal to 0, then we know that the result should be in the top half of this circle. So if that's what happens, then we can conclude that b, the bit we wanted to encrypt, must be equal to 0. And otherwise, if the bit is closer to q/2, then we have a guarantee that the bit must have been equal to 1. Hence, we recover the message that we wanted to encrypt, the bit b. And again, great success. So at this point, I reached my conclusion, but I want to just stop at this point and ask if there are any questions, because I see that we actually do have some time left, and I'm afraid I might have rushed all of these calculations a bit. So is this clear, understandable, or did I completely lose you along the way?
I think it was quite nice and clear.
All right.
I'm not sure if I have any questions. I mean, the idea seems to be very clear. I mean, now with ChatGPT and all these AI methods, I'm just thinking, how do you make sure that you somehow that it's not possible to brute force a way in there? Is there any thoughts on this?
Exactly. So that is a good segue to my concluding thoughts down here. First of all, there are many optimizations, variations, and generalizations that I have not mentioned here. So I'll just, since I actually have the time to do so, I'll mention one very common optimization, which is that this value 2n beta squared plus beta, we calculated it in the worst case. But you can show that actually hitting the worst case is exponentially small likelihood to happen. So you can set your parameters with much nicer bounds, which people usually do, and then you can still be guaranteed that you hit within the much looser bound, or much tighter bound, I would say, within, for instance, a guarantee that it will only happen, you will only go outside of that bound 1 out of 2 to the power 128 times or something like that. And then you get much more efficient systems, but the price that you pay is that sometimes, very rarely, but sometimes, a receiver will get an honestly generated ciphertext that they are unable to decrypt. And this could actually lead to security issues, not to mention, practicality issues. But this is why what we have shown so far is that the scheme satisfies perfect correctness. But if you tighten up this bound for efficiency gains, you get something, you get essentially imperfect correctness, where with a tiny probability, decryption will fail. And this is the reason why. And this is something which is very particular to lattice schemes. So that is one optimization, and there are many variations. There are, instead of working over a ring as we have been doing now, which is ZQ, we could be working over fields and other algebraic structures. And also you certainly want to encrypt more than one bit, right? So there are constructions that allow you to do this as well, to encrypt longer messages and make them more practical. What remains to be done, and what we haven't done so far, is to prove security. And when I say prove security, what I mean is that we need to prove that the construction we came up with is as hard to break as the underlying assumption is hard to solve, so that you get a tight relation between, so what was the underlying assumption? If I here it is. In the underlying assumption is the one I have highlighted here. It is that you can't distinguish between what's on the left-hand side and what's on the right-hand side. In order to prove security, you have to show that somebody who is able to break our system must necessarily be able to solve this problem. And we haven't done that at all, but that is much closer to my own research. then you have to analyze the underlying assumption itself in order to gain confidence that it is actually hard to solve, right? So first thing you could do, of course, is to try and brute force by checking all possible short vectors or all possible S's until you find one that satisfies the constraints and gives you back the public key, right? If you manage to go through the entire search space of possible private keys and you find one that gives you the public key, then you're done. But this is, of course, this will take exponential time, obviously. There are several attack routes that are better than exhaustive search. I think some of them are sub-exponential, but that might depend a little bit on the system and the underlying assumption and so forth. But what is particular about them is that none of the best known attack routes can be significantly sped up by polynomial speed up quantum algorithms, like, for instance, Grover's algorithm or quantum random walks or stuff like this. And I say significantly here because some of them have achieved like some tiny bits of speed up, but nothing like the squared speed up of Grover's algorithm. So modulo those tiny speed ups that will probably drown in the error correction overhead anyway, the best known attacks are actually classical algorithms. But the search for quantum speedups continues, which is not my field of expertise, but there are definitely people out there looking for this. And of course, the search for better classical algorithms is also, very active research. But both of these have been very active research for a while now, something like 20 years, and we still haven't reached any sort of breakthrough. Many lattice problems are actually known to be NP-hard, not necessarily the ones that we built our crypto system on. I'm a bit unsure about that, but it does give some hope that it will actually be hard in general to solve these underlying assumptions, both for classical computers and quantum computers, as we don't expect quantum computers to be able to solve NP-hard problems. And with that, I see that it is 12 o'clock, and I thank you for your attention.
Thank you very much. There was one question from Floris. He said, I suppose that you also need to know that R transposed A inverse E is almost never small. Otherwise, you could break this by inverting A.
Yes, that is a correct observation. And by setting the parameters to be large enough, I believe that this will happen with very high likelihood, that it is completely negligible, the likelihood that you will get small vectors by accident, essentially.
Okay, thank you. So are there any more questions?
Alexandra,
you had a question?
Yeah, I have a question. So so you mentioned in the end, like that I mean, there are some of these lattice problems that are NP-hard, but these are not the ones that you build your crypto system on, right? So in the end, like it's still unclear, like so I was asking, like, so presumably if you had a quantum computer that you could program and that you can play around with, would you imagine that you could find new attacks to these schemes, or how confident are you that you based purely on theory can somehow say something that you so, because as I see it for the classical crypto systems, much of the security, or that you believe that RSA, for example, is classically secure, is based on that it has been out there for so long and that people have tried to attack it with all the knowledge that they have. So if you now think of this post-quantum system, so if you can you comment? Yeah, can you comment on this?
Yeah, sure. Regarding the first point with the NP hardness, the short answer is that I'm not entirely certain. I tried looking into this yesterday because I find it to be an interesting point. There are some hardness problems that have been shown to be NP hard in the worst case, but not in the average case, which is what we need here, because we are sampling everything at random. And then there are others that are NP-hard in the average case. And then there are some that are in this NP intersect co-NP set, which is the same as factoring, right? Which is, you know, a red flag. I am simply not sure exactly what has been shown about the LWE assumption, but I would love to look into it and come back to you regarding that. But I am not a complexity theorist, which is why I'm not sure about this. Anyway, regarding the attacks, so this system is from around 2004, I think, which means that it's nearing up on 20 years of active classical analysis. And in particular, after the NIST PQC competition began a couple of years ago, this analysis effort was really intensified. And there is certainly a, let's say, fewer people looking at quantum algorithms for this than what one would want. And the reason for this is essentially that cryptographers don't know quantum computing, or few do, and people who know quantum computing rarely know cryptography. So there is sort of like a lacking intersect between the two communities for finding algorithms for solving lattice problems. There are people looking at this, just not as many as one would have hoped. In order to have full confidence in the security. What we can say is that the usual attack strategies of, for instance, Shor's algorithm, which is, you know, finding an abelian subgroup of a large group, or etc., are completely invalid here. And the usual attack strategy of just apply the Fourier transform and see what you get simply hasn't panned out so far. But people are still trying.
Mm-hmm.
Alexandra, you had a question?
Yeah, I think it's sort of similar or related to the one that was just asked. I just wanted to know if you know something. You said that in this NIST competition that they had certain hardness criteria. Do you know what those are? Or is it just like complexity theory?
Can you repeat the first part of the question?
It's a single question. It's if you know what the different hardness criteria for the competition were.
Right.
Or if it's just complexity theory.
It's not. So essentially what they did, which is a somewhat controversial choice, but it's one that has seemed to be working, is that they look at AES, which is, you know, the standard symmetric cryptography. So single key, and both sender and receiver has to use this key to encrypt and decrypt. It is very efficient, and it is used every day in conjunction with asymmetric cryptography in order to speed up the whole process. So what they say is that we have, after, you know, decades of research and analysis, we are very confident in the security level of AES. What we need for your system is for it to be at least as secure as AES with 128-bit keys. So that is for level 1, and each submitter was expected to give parameters for 3 security levels, I think. And I was for AES with 128-bit keys, and then 192, and then 256. Not sure whether they required 512-bit security as well, but a lot of people have that as well. And then the crypto systems remain the same, right? But you just increase these parameters like Q and N, where Q is a modulus, N is the dimension you're working in, and beta, which is the size of this error, etc. And you just tweak these parameters until you find that the best known attack against the underlying assumption takes as much time as it would take to break AES 128. What is ironic about this way of defining security, of course, is that as AES 128 gets analyzed and better attacks are discovered, even if it's just by a little bit, then the submissions are judged to be more secure without anyone having changed anything. So this is why it became a bit of a controversial choice. But that is how they define security in the competition.
Okay, thank you very much. I think we should stop here. Thanks for the nice presentation.
Thank you very much for the invitation.